Good afternoon, participants. I welcome you all to the day 5 session of Artificial Intelligence Tools for Accelerated Drug Discovery Program. I think Shaul sir is already in. Sir, can you start, sir?
Sure, sir. Sure. Yes.
Thank you, sir.
So, welcome everybody. Good afternoon. So, we will start our session now. So, today, like in the past few days, we have been discussing the different web tools. Okay. And then, we also saw some videos and other stuff related to how these neural networks and deep learning and all these machine learning algorithms work. Okay. Now, let us try make an attempt to practically code. Okay, so far we have been using software developed by other people for our sessions. Okay, now let us make an attempt to actually practically code. So I already told you, for practically coding any machine learning program, machine learning algorithm, we need to have certain tools. So one is the Python based tool. Okay, so we need a Python programming, and the thing is we also need certain interactive Python interpreters like Jupyter Notebook and all those things. Similarly, you have Anaconda, you have this pip install. So there are many related things. Okay. Similarly, the Python numerical library NumPy, Pandas, scikit-learn, these kind of additional add-on libraries also required for machine learning. Okay. So here we will actually make an attempt to use an online, Python interpreter called Jupyter Notebook. Okay, online Jupyter Notebook. So I'll try to share the screen and show to you. Just a minute. Okay, so this is actually like are you able to see the screen? Yeah, I hope you're able to see the screen now. Now,
Yes,
actually, this is GitHub. There is a software repository called GitHub. So GitHub contains several, source codes of many algorithms and popular programs. Okay, so machine learning codes also available, from very simple machine learning codes to advanced machine learning codes. Their source codes you can find here. So one can always retrieve this, download to your computer, and then you can practice it, edit it, and improve your machine learning capabilities. Okay, so GitHub is actually a repository, so you can go and see. They have um, uh, complete description about different programs, different machine learning programs. Now today we will try to use one of the most simplest machine learning tool called linear regression. Okay, linear regression, we generally use it in statistics, in many of the scientific data plotting. We use it without knowing that it is actually a type of machine learning algorithm. Okay, so it has been very common that we don't even recognize that it to be a machine learning algorithm. So simple, this linear regression actually, which is used to make the line of best fit for data plotting and all those things, is in fact one of the simplest types of machine learning algorithm. Okay, so what we will try to do, so before we we understand and code the convoluted neural network and advanced deep learning codes, let us try to first simply practically use Python coding for implementing this linear regression algorithm. Okay, so here we have this linear regression model. Okay, so we are going to use the interactive Python coding. Okay, so Python 3 will be best. So Python comes in two different flavors. One is Python 2 and Python 3. Python 3 is a recent one, but Python 2 still is used by a large number of people, so it's still there. So you can use now Python 3. So Python 3 can use, and then you can call libraries, numerical libraries in Python as add-ons. Okay, like NumPy, Pandas, MATLAB, Matplots. Okay, so Matplot library, all these libraries can be along with the Python package it comes. So you can source it. So and then you can implement this algorithm. So here we see the codes are very simple. We have to put a percentage symbol, matplot library inline. Then you import from NumPy, import asterisk, import matplotlib.pyplot as PLT. So it's actually basically like some initial statements you're making. So what we'll do, we will go to this. For example, this tool is there. So what I will do, I'll just delete all these things and redo it. Okay, so this is a Python this thing. So how to go is like I'll type again maybe. You can go to this online. You can type online Jupyter Notebooks. Okay, so this online Jupyter Notebooks actually web-based, open source web-based application that actually helps you to create and share documents that contains live machine learning codes, equations, and visualizations. Okay, so you can go to this online, the third option, online Jupyter Notebooks, calculator, so CALC. So you can go here, collaborative calculation in data science. This actually offers you a free web page, free online tool called Jupyter Notebook. So here you can yeah. So once you go here and click this run Jupyter Notebook, then you'll get this. Okay, so you say go to this, then it comes here. Okay, so you can go to the this Python notebook. So you can select the notebook. So you can notebook can select it, and then you can select Python 3. Okay, so Python 3. So if you click here, it suggests different kernels. So you suppose you are using R. Okay, so R is also one of the popular machine learning language. So you can choose R or Python, which are very popular. And even like for example, the Sage Maths and all those things are there. So we will use Python today. Okay, Python 3. Okay, so click on Python 3. So Python 3 will be the one just using this codes. Now you will have these inputs here where you can enter those statements. Okay, interactively. So the thing is, what I'm going to do, just since you're all new to this one, I'm just going to cut, copy, paste. So whatever statements I told now, like importing the NumPy libraries and this matplot libraries. Okay, so that one, what we'll do, we will try to we will try to put it here. Okay, so come here. That's the one. Yeah, here. So I'm going to just paste it here. You can just type it. Okay, since to save time, it will take 2 hours to type one by one. So I'm just like, since I'm demonstrating an example, I'm just doing this. So this is how to give the statement. Okay, so this is basically Python programming. That's all. So, but here the advantage is instead of using a terminal to execute this Python codes, we can use actually this Jupyter Notebook. So we can plot, we can visualize, you can make adjustments and all those things you can do here interactively. Okay, so here if you see run cells, Okay, if we click on run cells, so what it does, it's now taking this inputs. Okay, so now the input is now made. So now next what you'll do, the next bit of thing. Now what you're trying to say is we have got to demonstrate this linear regression, we need some data. Na? So the data is there. The data is written in a CSV format. So it's comma separated. Okay, CSV means comma separated values. So here the delimiter is the comma and the data set is data.csv. So here what they are trying to do is they're trying to assign those values to this variable called points. Points is equal to generate from text, data.csv delimiters comma. So like that we are giving statement, and then we are extracting those values. Okay, into, for example, once the point is variables are made, then we are trying to extract the, you have two columns now, the x and y. Okay, so the x will be actually to x and y will is assigned to y. So that is why the zeroth column and the first column. So zeroth column, whatever values are there, that will be that array will be assigned to x, and whatever is there in the next column, that will be that array. That array is made into a y variable. Okay, then we do a scatter plot. So we are using the matplot library to make the scatter plot of x and y. So x will be the variables and y will be the x is actually the one of the variable and y is the dependent variable. So trying to see the relation between them. Okay. So for example, here we can say like we can say like, for example, the drug concentrations activity. Like here they given different example. We can say a drug, for example, a particular drug's concentration versus the activity. The drug concentration is more, the activity will be more, like that. Okay, so we are trying to see a relation between the activity of the drug and the, so how to code this? So what I'll do, to save time, I'm just copying and pasting it here. But it is very easy. These statements are very easy. Okay. So first, before that, I have to import the data. Okay, so the data file should be imported, because when it comes to all this Python programming and all this machine learning, data is the most valuable one. Okay, so the data should be curated and properly handled, and it should be accessed by that algorithm. So you have to import the data. So how to import the data here is go to files, then there is an option called upload. Go to upload, and then here you click on this upload here. Then you can upload. So I have saved it in a folder called machine learning. So this data.csv is there. You can see the data.csv. So this file I am actually comma separated values. This file I am opening. Okay. So data.csv is open, and then I can actually access that. Okay. So this is how we have to upload the data first. So once we upload the data, we can come back to the codes. Now I'm going to actually do the coding. I mean make the plot. So I'm going to first so first the X label I can make it as drug concentration. Okay, drug concentration, and then this one is the activity. So just to make it related to our work, I'm just doing this. It's a very simple code. So you know that when the drug concentration increases, the activity also increases. So they have a dependence. So the activity is dependent upon drug concentration. So we are trying to just to use that two variable system. Okay. So and then we are trying to implement this simple linear regression. Now what I do, I have to go, since already I have imported the uploaded the data file. Okay. And then I already told you what are the meaning of these things. Now what I'm going to run this. For running this, I have to click this button. Okay. So when you run this data set is plotted. So you can see drug concentration in the y-axis. For example, you can imagine it is a mg per liter, something like that. Okay. So the drug concentration, or you can see in millimoles, like that. You can consider micromolar, millimolar, like that. So you have drug concentration in the x-axis and the activity is in the y-axis. So you can see that as the drug concentration increases, the activity increases. Okay. So here, this particular thing, Okay, now this now somebody is asking, sir, how the data will look like. So the thing is, the data is simple data file. Like for example, we are getting from some previous experiment or something like that. Okay, so generally now the simple linear regression, the data we get from some kind of observation, some kind of experiment. So here, if you ask me, sir, what is the data? The data is simple. So you can go and get it here. We come here now, data.csv. So this is the data. Okay, so you have the x and y. So you can see the maybe the first row, first column maybe the drug concentration, second column maybe the activity. Okay, so we have CSV file. This only I saved as the data at CSV and uploaded to that particular Jupyter notebook. Okay, so now having uploaded this one, you just imagine some kind of experiment study was done. Nowadays you can go to many of these university web pages or this kind of databases, so where you can download data sets, experimental data sets. Somebody must have done an experimental study and deposited things there. So you can use that for training your model and all those things. Understood? Na? So the thing is that's why like we have taken this data from the okay. Okay, just renaming data set is data set, that you can change it. That's not a problem. So drug means, like for example, in like plot the data set is there. Now we can data set is the data set. Okay, whatever the data has been acquired. Okay, so why to name it as drug? Data is data, na? So what we'll do is now, so we got the data set plotted. Okay, now what we can do, next one. So the next one will be the defining the hyperparameters, which are actually the ones used in machine learning. Okay, so when you come to this hyperparameters, you have to set the learning rate. Okay, so that means you have to expose the data to the algorithm and train it. So the thing is, if the exposure is too fast or too less, and you set a very high learning rate or a very low learning rate, it will not actually learn properly. So the thing is, sometimes too fast learning rate if we give, then actually training will be difficult. Okay, if suppose the learning rate is very slow, then it will take a lot of unwanted time and you waste time. So instead of accelerating, it will decelerate. So the learning rate has to be set, and we can actually interactively change the learning rate. Okay, the learning rate is actually a hyperparameter for the machine learning algorithm. Then now any kind of scatter plot and any kind of regression will have the slope and the intercept, y-intercept. So that is why we have to initially set the y-intercept to be 0 and the slope to be 0 initially to start with. Okay, so it's just a straight line initially start with. Then we are going to move it here and there and try to find the line of best fit. So initially we are trying to assign b is equal to 0 and m is equal to 0, and then in 10 iterations, so iteratively it will actually find the optimal value. Okay, so that iteration we are giving as 10. So first now define the hyperparameter. So go here, just plot the write down the hyperparameters. So you can whatever you are commenting out now will not be made to statement. So the remaining of statements, learning rate you're setting as 0.001, the slope you're setting as 0, the m is setting as 0, iteration is 10. Okay, so you are actually now feeding into the this whatever you set now, you're feeding into the algorithm. Now it's got this. Now what you'll do, now we have to the error costs. So the thing is, whenever you're trying, for example, you're moving that from m is equal to 0 and b is equal to 0, you're trying to move it to some value. Okay, then for example, you're trying to fix it as m is equal to 1, b is equal to 1, like that. So there, at that particular thing, the error values will be calculated. So how much it is deviant. Okay, so the error cost will be calculated. For that, some mathematical formulas are involved. That is what is given here. You can see here. Okay, so they're computing the error cost. Okay, so here the error cost is defined as this one. Can you see here? This is the formula. Okay, for calculating the error cost. So here what you will do, so we are defining the compute cost. Okay, so for example, suppose you're having some wrong value, the computational time cost will be more. So that's why we have to calculate the cost function. So here, what we do, we paste this one. Define compute cost as function of b, m, and points. Total cost initially 0. Total cost 0. N is equal to float length of points. So you already know you define points. Now what is points? Points is nothing but, what is points? You generated here. Points is nothing but the data.csv. Okay, all the values are taken from the data.csv. That is the points. Okay, so here how many entries are there? The length. So that length as a float, you are actually assigning to a value called n. Okay, so basically you're trying to, when you're trying to average, you have to know the number of points. So n is equal to float into length of points you're giving. Now compute sum of squared errors. So this is what you're trying to do. So for I in range 0 to length of points. So the thing is, for example, when you open this data.csv, that is data.csv. Yeah. So this, you can see now how many points are there. There are 100 points. Okay. So from 0 to 100. Okay. So you have to actually define that one. Okay. So that is what you are defining. 0 to length of points. Okay. Range. So the x is nothing but the what is x? So I told you there are two columns. One is 0th column, the first column. So whatever you have here is a 0th column, and this is the first column. So whatever values are here is made into an array and assigned to x, and whatever is here in the first column, that is actually made into an array and fed into the variable y. So that's how they defined it. So so we are putting as once again. Yeah, can you see here? I comma 0, points I comma 1. Okay, so this is how we assign the points, those variables. Now we have to do the cost calculation. Total cost. Total cost is equal to y minus mx plus b into 2. Okay, so this is how the cost is calculated. So if you want, you can go under detail. You can actually, you know, there are many data science books. You can refer to these mathematics behind it. Okay, so for example, costs of error in ML. So cost function. So there are many. So for example, cost function coding. If you see. You can have excellent articles here, so you can go and see. So cost function. So cost function, it is a function that measures the performance of a machine learning model for a given data. Okay, so the cost function quantifies the error between predicted values and the expected values and presents it in the form of a single real number. Okay. So the thing is, for example, if the predicted value and expected value, the difference is minimal, cost function will be minimal. Okay. If the error is more, that means the difference between the predicted value and the expected value is a huge, like more. Then that means the cost function will be more. That means the algorithm will perform poorly. So the thing is, it is not able to, because the main essence is the regression algorithm is to predict the value. Understood now? So you have classifiers, you have regressors. So classifiers try to classify the given input into either this category or that category. But regression models, what they try to do, they try to predict the value. Okay. So here the predicted value should be as minimal deviant from the expected value. So this cost function actually measures that. It quantifies the error between the predicted value and the expected value and presents it in the form of a single real number. Depending on the problem, cost function can be formed in many different ways. The purpose of cost function is to be either minimized. So the thing is, we try to minimize the cost function. Okay. So in most cases, that is the thing. So minimize, then return the values usually called cost or loss. This is what we are trying to do here in this particular thing. We are trying to minimize. Okay. So the goal is to find the values of model parameters for which the cost function return as small number as possible. Okay. So here we need to, for example, you can have a, for example, suppose you are trying to do protein folding. Okay. So there, what will be the cost function? So the thing is, we are trying to minimize the energy basically. Okay. The thing is like, suppose you are able to minimize it. Okay. That means the cost function will keep on decreasing. Okay. So the cost function will be minimal. So generally, if the machine learning model that you're using, whatever like deep network or a regression model or simple linear regression, whatever you're using for some predicting the value, if that model is correct, okay, you have a number of machine learning algorithms. So which model will be better for you? You can actually get an idea by calculating the cost function. Okay, so the various things are there, so and various formulas also there. So you can go and actually read these articles. Okay, so to calculate the cost function. Okay. Now, so this is what is implemented here as cost function. Okay, this one. Now, what we're trying to do, we'll after making the definitions here, we'll try to enter it. We'll try to enter the algorithm. Now, gradient descent functions. Now here gradient descent. Okay, so the thing is now the line has to be moved here and there, adjusted in several iterations, so that the cost function gets made. Once we have defined the cost function, we now try to do a gradient descent minimization. Okay, the gradient descent minimization plays an important role. Even in AlphaFold protein folding problem, there also the gradient descent minimization is used. So the thing is like you know about simulated annealing, you know about other methods of energy minimization. So similarly, this gradient descent energy minimization also is quite popular. It's called stochastic gradient descent energy minimization. So here, what they try to do is this: they define the gradient descent, so that whatever slope you had initially, so you're trying to move, assign different values. Okay. And then you try to change in several iterations, you're trying to change those values and then explore the cost function for each case. And then trying to find out which is the best, that means which is the least cost function, that will be the best line of fit. Okay. So you're trying to define that one. So again, there's a little bit of mathematics is involved. So we are assigning B, the starting B, M is called starting initially, and then the cost graph we are calculating. So you can see, you know, like it's all very simple to understand. Like what is this? So everything is given here. So what I do is just copy this one. Okay, and I'm going to paste it here. Okay. So suppose you do not know what is gradient descent minimization, I have a small video I'll show you. Yeah. So gradient descent minimization, what is that? Yeah. The stats question, one of the very popular.
Hi, I'm Brad Cowan, and in this video, I'm going to show you how anyone can quickly and easily create Google videos, just like the one you're watching right now.
Gradient descent is decent at estimating parameters. StatQuest. Hello, I'm Josh Starmer and welcome to StatQuest. Today we're going to learn about gradient descent and we're going to go through the algorithm step by step. Note, this StatQuest assumes you already understand the basics of least squares and linear regression. So if you're not already down with that, check out the quest. In statistics, machine learning, and other data science fields, we optimize a lot of stuff. When we fit a line with linear regression, we optimize the intercept and the slope. When we use logistic regression, we optimize a squiggle. And when we use t-SNE, we optimize clusters. These are just a few examples of the stuff we optimize. There are tons more. The cool thing is that gradient descent can optimize all these things and much more. So if we learn how to optimize this line using gradient descent, then we'll have learned the strategy that optimizes this squiggle and these clusters, and many more of the optimization problems we have in statistics, machine learning, and data science. So let's start with a simple data set. On the x-axis, we have weight. On the y-axis, we have height. If we fit a line to the data, and someone tells us that they weigh 1.5, we can use the line to predict that they will be 1.9 tall. So let's learn how gradient descent can fit a line to data by finding the optimal values for the intercept and the slope. Actually, we'll start by using gradient descent to find the intercept. Then, once we understand how gradient descent works, we'll use it to solve for the intercept and the slope. So for now, let's just plug in the least squares estimate for the slope, 0.64. And we'll use gradient descent to find the optimal value for the intercept. The first thing we do is pick a random value for the intercept. This is just an initial guess that gives gradient descent something to improve upon. In this case, we'll use 0, but any number will do. And that gives us the equation for this line. In this example, we will evaluate how well this line fits the data with the sum of the squared residuals. Note, in machine learning lingo, the sum of the squared residuals is a type of loss function.
This is what you're calculating, sum of the squared residuals. Okay, so that means you are trying to find this difference. Okay, and then find and take a sum and square that. Okay, so that is what actually is defined here. If we come here to that GitHub code, what they're saying, y minus m into x plus b, when they put star asterisk 2, what is the meaning? It's actually to the power 2. If they put asterisk 2 means into 2, asterisk into asterisk 2 means what? They put the star 2 times, it means it's the power 2. Okay, so that is what they're trying to do here. So they're trying to find this difference and then sum it up and then square it. So that is sum of squared errors. Okay, so that is what is actually is explaining, sum of the squared residuals. Okay, so this difference. Okay.
We'll talk more about loss functions towards the end of the video. We'll start by calculating this residual. This data point represents a person with weight 0.5 and height 1.4.
You just imagine instead of weight and height, drug concentration and activity, like what we are taking the example of this.
We get the predicted height, the point on the line, by plugging weight equals 0.5 into the equation for the line. And the predicted height is 0.32. The residual is the difference between the observed height and the predicted height. So we calculate the difference between 1.4 and 0.32. And that gives us 1.1 for the residual. We'll keep track of the sum of the squared residuals up here. Here's the square of the first residual. The second residual is 0.4. And the third residual is 1.3. In the end, 3.1 is the sum of the squared residuals. Now, just for fun, we can plot that value on a graph. This graph has the sum of squared residuals on the y-axis and different values for the intercept on the x-axis. This point represents the sum of the squared residuals when the intercept equals 0. However, if the intercept equals 0.25, then we would get this point on the graph. And if the intercept equals 0.5, then we would get this point. And for increasing values for the intercept, we get these points. Of the points that we calculated for the graph, this one has the lowest sum of squared residuals. But is it the best we can do? What if the best value for the intercept is somewhere between these values? A slow and painful method for finding the minimal sum of the squared residuals is to plug and chug a bunch more values for the intercept. Ugh. Don't despair. Gradient descent is way more efficient.
So for this only, we are trying to use the gradient descent emission. Okay, in linear regression, why it's used? You want to try to find the optimal, the minima here. Okay, so which one is the most least? So here you are plotting sum of squared residuals, that is the error values versus the intercept. Intercept versus this one. So then you try to find out the, using gradient descent emission, try to find out the minima.
For finding the minimal sum of the squared residuals is to plug and chug a bunch more values for the intercept. Ugh. Don't despair. Gradient descent is way more efficient. Gradient descent only does a few calculations far from the optimal solution and increases the number of calculations closer to the optimal value. In other words, gradient descent identifies the optimal value by taking big steps when it is far away and baby steps when it is close. So let's get back to using gradient descent to find the optimal value for the intercept, starting from a random value. In this case, the random value was 0. When we calculated the sum of the squared residuals, the first residual was the difference between the observed height, which was 1.4, and the predicted height, which came from the equation for this line. So we replaced predicted height with the equation for the line. Since the individual weighs 0.5, we replace weight with 0.5. So for this individual, this is their observed height, and this is their predicted height. Note, we can now plug in any value for the intercept and get a new predicted height. Now let's focus on the second data point. Just like before, the residual is the difference between the observed height, which is 1.9, and the predicted height, which comes from the equation for the line. And since this individual weighs 2.3, we replace weight with 2.3. Now let's focus on the last person. Again, the residual is the difference between the observed height, which is 3.2, and the predicted height, which comes from the equation for the line. And since this person weighs 2.9, we'll replace weight with 2.9. Now we can easily plug in any value for the intercept and get the sum of the squared residuals. Thus, we now have an equation for this curve, and we can take the derivative of this function and determine the slope at any value for the intercept. So let's take the derivative of the sum of the squared residuals with respect to the intercept. The derivative of the sum of the squared residuals with respect to the intercept equals the derivative of the first part plus the derivative of the second part plus the derivative of the third part. Let's start by taking the derivative of the first part. First, we'll move this part of the equation up here so that we have room to work. To take the derivative of this, we need to apply the chain rule. So we start by moving the square to the front and multiply that by the derivative of the stuff inside the parentheses. These parts don't contain a term for the intercept, so they go away. Then we simplify by multiplying 2 by -1. And this is the derivative of the first part. So we plug it in. Now we need to take the derivative of the next two parts. I'll leave that as an exercise for the viewer. Bam! Let's move the derivative up here so that it's not taking up half the screen. Now that we have the derivative, gradient descent will use it to find where the sum of squared residuals is lowest. Note, if we were using least squares to solve for the optimal value for the intercept, we would simply find where the slope of the curve equals 0. In contrast, gradient descent finds the minimum value by taking steps from an initial guess until it reaches the best value. This makes gradient descent very useful when it is not possible to solve for where the derivative equals 0. And this is why gradient descent can be used in so many different situations. Bam. Remember, we started by setting the intercept to a random number. In this case, that was 0. So we plug 0 into the derivative, and we get negative 5.7. So when the intercept equals 0, the slope of the curve equals negative 5.7. Note, the closer we get to the optimal value for the intercept, the closer the slope of the curve gets to 0. This means that when the slope of the curve is close to 0, then we should take baby steps because we are close to the optimal value. And when the slope is far from 0, then we should take big steps because we are far from the optimal value. However, if we take a super huge step, then we would increase the sum of the squared residuals. So the size of the step should be related to the slope, since it tells us if we should take a baby step or a big step, but we need to make sure the big step is not too big. Gradient descent determines the step size by multiplying the slope by a small number called the learning rate. Note, we'll talk more about learning rates later. When the intercept equals 0, the step size equals negative 5.7. With the step size, we can calculate a new intercept. The new intercept is the old intercept minus the step size. So we plug in the numbers, and the new intercept equals 0.57. Bam! In one big step, we moved much closer to the optimal value for the intercept. Going back to the original data and the original line, with the intercept equals 0, we can see how much the residuals shrink when the intercept equals 0.57. Now let's take another step closer to the optimal value for the intercept. To take another step, we go back to the derivative and plug in the new intercept. And that tells us the slope of the curve equals negative 2.3. Now let's calculate the step size. By plugging in negative 2.3 for the slope and 0.1 for the learning rate. Ultimately, the step size is negative 2.3, and the new intercept equals 0.8. Now we can compare the residuals when the intercept equals 0.57 to when the intercept equals 0.8. Overall, the sum of the squared residuals is getting smaller. Notice that the first step was relatively large compared to the second step. Now let's calculate the derivative at the new intercept, and we get negative 0.9. The step size equals negative 0.09, and the new intercept equals 0.89. Now we increase the intercept from 0.8 to 0.89. Then we take another step, and the new intercept equals 0.92. And then we take another step, and the new intercept equals 0.94. And then we take another step, and the new intercept equals 0.95. Notice how each step gets smaller and smaller the closer we get to the bottom of the curve. After 6 steps, the gradient descent estimate for the intercept is 0.95. Note, the least squares estimate for the intercept is also 0.95. So we know that gradient descent has done its job, but without comparing its solution to a gold standard, how does gradient descent know to stop taking steps? Gradient descent stops when the step size is very close to 0. The step size will be very close to 0 when when the slope is very close to 0. In practice, the minimum step size equals 0.001 or smaller. So if this slope equals 0.009, then we would plug in 0.009 for the slope and 0.1 for the learning rate, and get 0.0009, which is smaller than 0.001, so gradient descent would stop. That said, gradient descent also includes a limit on the number of steps it will take before giving up. In practice, the maximum number of steps equals 1,000 or greater. So, even if the step size is large, if there have been more than the maximum number of steps, gradient descent will stop. Okay, let's review what we've learned so far. The first thing we did is decide to use the sum of the squared residuals as the loss function to evaluate how well a line fits the data. Then we took the derivative of the sum of the squared residuals. In other words, we took the derivative of the loss function. Then we picked a random value for the intercept. In this case, we set the intercept to be equal to 0. Then we calculated the derivative when the intercept equals 0, plugged that slope into the step size calculation, and then calculated the new intercept, the difference between the old intercept and the step size. Lastly, we plugged the new intercept into the derivative and repeated everything until step size was close to 0. Double bam! Now that we understand how gradient descent can calculate the intercept, let's talk about how to estimate the intercept and the slope. Just like before, we'll use the sum of the squared residuals as the loss function. This is a 3D graph of the loss function for the different values for the intercept and the slope. This axis is the sum of the squared residuals. This axis represents different values for the slope, and this axis represents different values for the intercept. We want to find the values for the intercept and slope that give us the minimum sum of the squared residuals. So, just like before, we need to take the derivative of this function. And just like before, we'll take the derivative with respect to the intercept. But unlike before, we'll also take the derivative with respect to the slope. We'll start by taking the derivative with respect to the intercept. Just like before, we'll take the derivative of each part. And just like before, we'll use the chain rule and move the square to the front and multiply that by the derivative of the stuff inside the parentheses. Boop, 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 boop. Since we are taking the derivative with respect to the intercept, we treat the slope like a constant, and the derivative of a constant is 0. So we end up with -1, just like before. Beep, boop. Then we simplify by multiplying 2 by -1. And this is the derivative of the first part. So we plug it in. Likewise, we replace these terms with their derivatives. So this whole thing is the derivative of the sum of squared residuals with respect to the intercept. Now let's take the derivative of the sum of the squared residuals with respect to the slope. Just like before, we take the derivative of each part. And just like before, we'll use the chain rule to move the square to the front and multiply that by the derivative of the stuff inside the parentheses. Beep, 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 boop. Since we are taking the derivative with respect to the slope, we treat the intercept like a constant, and the derivative of a constant is 0. So we end up with -0.5. Boop, boop. Then we simplify by moving the -0.5 to the front. Note, I left the 0.5 in bold instead of multiplying it by 2 to remind us that 0.5 is the weight for the first sample. And this is the derivative of the first part. So we plug it in. Likewise, we replace these terms with their derivatives. Again, 2.3 and 2.9 are in bold to remind us that they are the weights of the second and third samples. Here's the derivative of the sum of the squared residuals with respect to the intercept, and here's the derivative with respect to the slope. Note, when you have two or more derivatives of the same function, they are called a gradient. We will use this gradient to descend to the lowest point in the loss function, which, in this case, is the sum of the squared residuals. Thus, this is why the algorithm is called gradient descent. Bam! Just like before, we'll start by picking a random number for the intercept. In this case, we'll set the intercept to be equal to 0. And we'll pick a random number for the slope. In this case, we'll set the slope to be 1. Thus, this line, with intercept equals 0 and slope equals 1, is where we will start. Now let's plug in 0 for the intercept and 1 for the slope. And that gives us two slopes. Now we plug the slopes into the step size formulas and multiply by the learning rate, which this time we set to 0.01. Note, the larger learning rate that we used in the first example doesn't work this time. Even after a bunch of steps, gradient descent doesn't arrive at the correct answer. This means that gradient descent can be very sensitive to the learning rate. The good news is that in practice, a reasonable learning rate can be determined automatically by starting large and getting smaller with each step. So, in theory, you shouldn't have to worry too much about the learning rate. Anyway, we do the math and get two step sizes. Now we calculate the new intercept and new slope by plugging in the old intercept and the old slope and the step sizes. And we end up with a new intercept and a new slope. This is the line we started with, and this is the new line after the first step. Now we just repeat what we did until all of the step sizes are very small or we reach the maximum number of steps. This is the best fitting line with intercept equals 0.95 and slope equals 0.64, the same values we get from least squares. Double bam! We now know how gradient descent optimizes two parameters, the slope and the intercept. If we had more parameters, then we just take more derivatives and everything else stays the same. Triple bam! Note, the sum of the squared residuals is just one type of loss function. However, there are tons of other loss functions that work with other types of data. Regardless of which loss function you use, gradient descent works the same way. Step 1. Take the derivative of the loss function for each parameter in it. In fancy machine learning lingo, take the gradient of the loss function. Step 2. Pick random values for the parameters. Step 3. Plug the parameter values into the derivatives, the gradient. Step 4. Calculate the step sizes. Step 5. Calculate the new parameters. Now go back to step 3 and repeat until step size is very small or you reach the maximum number of steps. One last thing before we're done. In our example, we only had 3 data points, so the math didn't take very long. But when you have millions of data points, it can take a long time. So there's a thing called stochastic gradient descent that uses a randomly selected subset of the data at every step rather than the full data set. This reduces the time spent calculating the derivatives of the loss function. That's all. Stochastic gradient descent sounds fancy, but it's no big deal. Hooray! We've made it to the end of another exciting StatQuest. If you like this StatQuest and want to see more, please subscribe. And if you want to support StatQuest, well, consider buying 1 or 2 of my original songs or buying a StatQuest t-shirt or hoodie. The links to do this are in the description below. All right, until next time, quest on.
If you write anything on your computer, you need to get Grammarly.
I write pretty much all day, every day, and Grammarly makes my writing better.
As a student, I like that it's free.
It actually is correcting everything.
Hello, Shahul sir.
Grammar errors, spelling errors, and even helps me find the right words to use so I can say what I want to say.
It catches all those embarrassing little.
Mean square error, cost function, gradient descent, and learning rate. These are some of the important concepts.
Yeah, many more excellent videos available. But I think now you got an idea about this cost function and also the gradient descent animation. Okay, so now we'll go and continue our exercise. Okay, so this is the one. Okay, so now you understood the mathematical meaning behind all those things. Okay, so now what we'll do, we'll try to run this one. Okay, so we try to run the gradient descent and then try to get the OT-based B and M value. So right now we are 0 for B, both B and M. So you are now going to run this gradient descent and then you are trying to optimize B and M. So what you do, you come here. Okay, so run this one. They are defined. So I just left this one. That's why it's not done. One second. Oh, we first we have to I forgot to. I showed the video but I forgot to execute this one. So one second, because we didn't define this gradient, that's why. So this one I'm removing. So we defined compute cost. Now I showed the video for gradient descent. Now we have to define that one. So this is the definition. Okay, so now it's defined. Now you can go and get this one. Points is not defined. I will define here now. Defined. you have to refresh. The long gap we are giving now, so small memory problem. Okay, so finally it has got the optimized value. Can you see? Optimized B and optimized M. And the B is 0.029 and the optimized slope is 1.477. Y-intercept is 0.029 and M slope is 1.477. So finally the cost is actually reduced to 112.653. Okay, so here to come to the minimized cost, we have to try to find the optimal minima for the cost function. So that is why we use gradient descent, and finally we got us 112.65. Now what we'll do, we will, once we got this optimized value, we'll plot cost per iterations. Okay. Plot the cost per iterations. Okay, so it's showing as we go now. I told them totally 10 iterations were given. So here, as you keep on improving the number of iterations, increase the number of iterations, the the algorithm actually works and tries to find the optimal minima for the cost function. Okay, so we can even try, like for example, like given this one, we can go and make some small changes. You can see, like suppose we go for 100 iterations, what happens? 100 iterations. So we will define everything again. Already it is reached. There's no use of going to 100 iterations. Simply I'm just trying. Okay. So very small differences there. See here. So there's no use. Clearly, you can see that within 10 iterations itself, it has hit the plateau. Okay, it has come down. The cost function has come down. That is why there's no need for 100 iterations. 10 iterations is more than enough. Okay, so like this, you can actually find out. Okay, yeah, it has reached actually you see here 6 to 6, I think in 8 iterations it has come down. 10 is I think more than enough. Okay, now what we will do, so they say actually in fact in 5 iterations it is reached. Okay, now you'll plot the line of best fit. So we'll plot the line of best fit. So what we do, paste. So since drug concentration versus activity. Okay, so trying to find the line of best fit. Okay, so now we have got the line of best fit. So this is how one can actually try to implement the simplest machine learning codes using this Jupyter notebook based Python coding, interactive Python coding, where you can, as you code, you can interactively change values, plot it, and you can edit it. So this is the advantage of using the online version of this Jupyter notebook. You can locally install also. You can go and install Jupyter notebook locally also in here, but you need I think a Unix computer. You need a Linux-based OS operating system to install Jupyter notebook. And other thing is like you also need to install other dependencies. It will take time, maybe like half an hour to 1 hour you have to waste to just install this Jupyter notebook. But online, like all the libraries can be accessed and it's very simple to use. So that's why it's just on this online tool. Thing is like you can try other codes also. Like you can go to GitHub. There are various codes. Okay. So I just demonstrated a simple code, and I showed you how to plot. Okay. So the thing is, you can go to and try in other machine learning codes. Like you have even how to build a neural network, a simple neural network. You have GitHub. Can you see? We have, for example, you come here, you can see all these different. We just use linear regression, something called logistic regression. Logistic regression means instead of drawing a line of best fit, use some kind of polynomial function, and then you use some kind of a non-linear curve to actually try to find the fit. Now, if you see here, instead of line of best fit, it will be like using a polynomial for getting the best fit. Now you have names based, KNN implementation, SVM, PCA. Okay, so you have several things actually. Okay, so even for PCA actually is principal component analysis. That is actually a important tool which is used in unsupervised learning. Okay, unsupervised learning, particularly it is used to reduce dimensionality of your data without seriously altering the pattern. Okay, without seriously altering the pattern in your data, it can be used to reduce the dimensionality of the data. Also, PCA can be used to extract important features. Okay, so the thing is, you can use PCA basically to on unlabeled data and then do feature extraction, build up a labeled data using that one. Okay, so SVM is support vector machine. That's a type of classifier. So you have excellent things. You can even see natural language processing, neural network, how to make a neural network. Simple codes are there. Okay, so you can go and you try yourself. It's an excellent source of thing. Okay, so you can examples are there, data files are there, download data files, upload them. Then you can use that code and then you can implement them. Okay, so try. In the free time you can try and okay.
Annotation, can you remove that annotation, sir?
Which one, sir?
Somebody, I think, drawn some annotation. Red color line was there.
I don't know, sir. Like it is there. Who's drawn? I don't know. Like it is not in my. It is not in my. Maybe you can stop share and again share. Can I do that
Okay,
one?
okay. I'm stop share.
Now it went, na?
Yes,
Hello?
sir.
Yeah. So thing is like you have various tools. Even I saw an excellent tutorial about PCA. PCA from Kaggle. You know, Kaggle also is for COVID-19 genome analysis. COVID-19 genome mutation prediction. So if you suppose, like asking these questions, how COVID-19 will mutate next. So the thing is now interesting things are there in Kaggle. That is also a repository for different like people, like-minded people now who are interested in machine learning codes. They can make the machine learning code, submit there, subject to review by others, and then edit that one, and they can come up with the new tools. So it's all open source machine learning tools. Okay. So thing is like you have. I saw some wonderful. Yeah, sequence. You can go here. You can find a lot of things actually. Even for drugs, also you can find it. Kaggle. Kaggle also like you can find many. Suppose you're a learner now, you can use it for you. You can go and download and then check whether that person has done right. Computational prediction of protein in COVID-19. Like for example, this can be considered in target identification. What all protein it codes COVID-19 from its genome. They have got a prediction tool. So many related to COVID-19. There are so many are there actually. Kaggle. COVID-19 and drug. COVID-19 drugs plus Kaggle. Topic is there. Data set is there. See? Drug review data set. See, here also is there. Coronavirus drug discovery data set. Like this is a code for actually like finding out number of publications. Like since a lot of papers are discussing about COVID-19 and the drugs, so it's like a search for that. Okay, so there are several, you can see several of these notebooks are available. So it's up to you to go and, you can do some, for example, see SARS-CoV-2 statistical analysis. So you want to learn something about this, so many resources available. So you can see here from the X-ray data how to predict, from the different scan data how to predict the coronavirus, whether it's positive or not. So you have these codes available. So you can try in the free time, you can sit and try all these things. Okay, so this. So this is a very similar approach, but using neural networks. What we saw is linear regression, and this is using neural network. Same the learning rate, cost function calculation, everything is there. You can try this also. Can you see it keeps on decreasing the cost function? Starts with around point, how much? 1.7, and then finally it becomes some 0.0 something like that. everything you can map, we can make GitHub. GitHub actually, see, GitHub is a repository. GitHub using for making heat maps and all, you can use this Jupyter notebook and this Python coding and all those things. There's all kind of graphical support now, so you can make it. GitHub is only the place where these codes can be found actually. Understood, na? So what you can try to do is type here simple neural network. Okay. So it's very good, simple tutorial available. Okay, so you can try to go and implement this one. So it's available as a Docker file. Okay, so Docker file means you have to install GitHub and run it. Docker files, GitHub Docker files. So you will see Python notebooks will be easy for us. So, monkey, sigma function. Yeah, these are Python libraries. So our whatever we have done, that is enough for explaining. So we have Docker, different tools are available for Jupyter Notebook, Docker. So here we are using this one. Okay. Simple. Okay, so now there are several tools available. In the free time you can go and see. I just showed you certain most easily accessible repositories which you can download and practice it. Okay, so that's what I was going through all those things. Now we will come to this DPubChem. This is one more tool for PSR modeling. Okay, which we didn't discuss last time. DPubChem is there. So DPubChem is a web-based tool, web server-based tool, and this can be used for predictive modeling. So here you can see you can build a model, then you can do start virtual screening. So what you can do is first we have to do model building for PSR. PSR model building is done. So this is actually based on some experimental data sets. Okay, so there are several data sets can be available from several repositories, several databases. So here if you see they have got it from PubChem bioassay database. Similarly, your PubChem CADs Then even that drug 2D text form can be given and then searched. So here we are actually going for PubChem bio database, PubChem bioassay database. So where different bioassays are done, and then what happens is they are giving the data sets to be accessed. Okay, so here high throughput studies, generally high throughput studies, experimental studies are done, and the data is available. So using that, we can actually frame a model. We can try to develop a QSAR model. Okay, using this machine learning algorithms. So once we develop this model, what we can try to do, we can actually, once we have trained and made a model, we can try to, using the predictive model, we can do virtual screening. Okay, so from a huge ligand database, computationally you can do virtual screening. So what is the advantage of doing this virtual screening aided by our AI tools is that it's actually much faster and the predictive power also is higher. Okay, so that is why we are going for a AI guided virtual screening. So now what I do is, last time I showed you deep screen. This is another tool, deep PubChem. Okay, so what you can do, you can select the database from which the data sets, external data sets obtained. So if we go now, each data set has a ID. Okay, wow. So for example, you can really go to this database, PubChem bio database. You can go, and then so PubChem bioassay database. So you can access those using different action numbers. Okay. Okay, so here you can go and access them. Now, for example, browse data, classification browser. Okay, so come here, and then you type PubChem bioassay database. PubChem bioassay ID 644. PubChem bioassay. PubChem bioassay. Database. Here it is 644. Okay, you can see the bioassay. You can see here now, bioassay. You type bio, you can see the bioassay here, and several bioassays will be there. So whatever is needed for you, you can take. So we can go for this COVID-19 related one. COVID-19. There are 10 assays available. Can you see here? Inhibition of the SARS coronavirus PL Pro. PL Pro means what? What is PL Pro? Papain-like protease. Okay, there are two important protease enzymes in COVID. One is the main protease, otherwise called as the chymotrypsin-like protease. 3CL protease, chymotrypsin-like protease. That is the main protease. There is one more protease called as the papain-like protease. Okay, so both are important targets. So they have got a bioassay for like this one. Okay, so 3CL protease. So they use luminescence assay. Okay, so you can see here the the study is here. Okay, now one more is there. You can see one more study is there. This is using 3CL Pro. This is the chymotrypsin-like protease, main protease. Okay, so there's one more study here, and then there's again the extension same study. And here you can see that antiviral activity, same targets. So this one you can see inhibition of SARS-CoV-3 cell protease expressed in E. coli by FRET assay. Okay, so this is a FRET assay based one. Okay, so they express the protein recombinantly and then subject to a biophysical assay using FRET. Okay, so this is the in vitro assay. So you can see here one more assay is there. Here ELISA based testing, inhibition of SARS-CoV PLA probe by microplatelet analysis. Okay, so we have several studies here. Okay, now what I will do, bioassay AID will type. This is for row kinase 2. Okay, so what we'll do, we have to put the correct say AID. So I am coming here and I am coming to this one. We can use for this FRET assay one. Okay, so you can copy this one. 725104. Bioassay ID is 725104. Please copy this one. 725. So 725104. 725104. So it's there. FRET assay. Okay. So they have tested some compounds, and then out of it, 17 have been found to be active. Okay, I think previously also I've shown such kind of thing, Q-FRET assay. Okay, so one more Q-FRET assay also showed. So Q-FRET assay for main protease of COVID-19. That is also available. That's a much larger study. Can you see here? 3-cell protease, same thing. Bioassay. I think this is a better study. You can see because they have done more, out of which 44 actives have been done. So like that, there are several available. So this is actually like this one. This is for avian Brocavirus. We will go for COVID-19 itself. COVID-19. This is also SARS coronavirus. For SARS coronavirus, so you can see here they have tried 380 compounds and they got 136 studies. So like that, you have several PubChem based thing are there. You can try them. Okay, if you go to deep screen, I think we have taken something similar to that one. Deep screen. Server. Deep screen. Yeah, deep screening Z-Lab. So here in this, there was a much bigger data set was used. So I'm trying to track the data set. Yeah, in this one, we last time, should we used a bigger data set? That's why I'm trying to do the same one. Okay, so one more thing. Go to this one, Chemprop. And Chemprop we used actually. One second. Chemprop. Good. So here, yeah, this one, yes, this data set. Yeah, this one. So this is a much bigger. Can you see? 290,000 compounds were tested. Out of 405 actives were done. So we can copy this one to train our model. We can copy this one 1706. So this will be better. 1706 because the much bigger data set. Yeah. So you can see the 405 actives and 290,893 tested compounds. So I think it's better to use this large data set. So we are using this ID and we are taking this one. And type of chemical features, this one is recommended. So we are using this one. There are like, for example, these are all different descriptors for your molecule, like how they can be vectorized into numbers, the molecule numbers. The molecules are drawn as a graph, and then the atoms represent the nodes and the bonds, the edges, and using this one features extracted. Okay, so feature selection method you can give like whatever it is default you can try initially. So classification model you can use random forest or you can use support vector machine. Different available neural network, decision trees. So you can try the recommended one, random forest. Okay. Actually, random forest actually is actually a type of when you have multiple decision trees. Okay, that becomes a random forest. So that is a classification model, and the tenfold the cost validation can be done. So you're selecting this one, and then you can give your mail ID optional. So in case any current cut is there, now it will be directly mailed to you because it's not going to run in your computer. It's going to be running in the server there. Okay. So voice.com. So I am just trying to build a model. What model? A QSAR model using the random forest machine learning algorithm. Okay, with the tenfold cost validation. And I am using this PubChem BioSA 1706. That is a Fred study done on a large number of molecules for screening active compounds against main protease of COVID. Okay, from this experimental data set, I'm going to build a QSAR model. And using that one, I'm going to perform virtual screening on a larger chemical library. Okay, so that is the essence. So build model. So what you can do, you can vary. Next time feature selection method, you can try PCA or something. Okay, so classification model you can try. So instead of random forest, you can use some other thing. It all depends on the data. Okay, sometimes the huge data, bigger data means certain neural networks can work properly, deep learning neural network. Simple data, simple algorithms can work better. So you can try and vary and see the prediction outcomes. Any questions also you can ask in between. I don't know why it's not working. It's running properly, right? Yeah, 1706, 1706. And then feature selection method. Okay, it's running. The job is running. Generally, this depub chem is suited for studies done on small, like 50,000 chemicals. Okay, but our data set contain 290,000 chemicals. Okay, that is why it's slightly slower. So that is why we can use this one. The other method, which is developed by MIT, ChemProp by MIT. So you can try this one. You can see that. They've got a source balance model. You can go for source balance, and then you can try the different drugs. So here already is trained. Which one? In this study, we are not training anything. Already they've trained data sets, trained models. Okay, so already the data set is taken and a model has been created. Okay, so they are used all these things, RD kit features and all those things, and ChemProp models are created. So we give only the new drug name. If you give a 2D representation, it will classify whether it's going to be active against that 3CL protease or not. That means already in this MIT based tool ChemProp, already the model has been built and is ready for our analysis. Okay, the only thing you need to use the input. That means a new compound you're putting. Okay, and evaluating the whether that will have any binding property or not. Okay, so that means here already the model has been trained against the active and inactive, and then it is now already capable of prediction. Okay, this depub chem we are doing in depub chem. What you're doing? We are doing that training is going on. Okay, we are building a model initially. Okay, it's going on. You see, in depub chem, I am trying to build a model initially. Okay, so in this case, what is happening? They already have a model. They already have a model, and they have actually trained it. It is actually like 99.1% positive, 99.9% negative. That kind of data set is taken and it's trained. So it's able to now predict a new molecule whether it's going to be active or not against the COVID-19. So just for checking, I'm just going to take some drug like lopinavir or something. Lopinavir or nelfinavir in drug bank. So just go and take the smiles format and I copy this one. I paste it here. Okay. So what I do, I say predict. So there's some error. I think last time also we did same thing. We're showing some error. Previously, we just give that immediately come. But I don't know if it's not working right now. Maybe you can draw even a draw molecule. Upload file. Even save this. Join DAY-5 smile. And then distance. Just to try whether this working is upload file, choose file, go to ML Microsoft all files. Just now we got now. What is it one? Lopinavir. That's nice. No, it's not working. There's some error in that server error. Okay. So the chemprop, I think it's not working. No problem. Like anyway, we're running this one. Na? 490. The same thing we can try with a smaller one. Maybe this one. This one. 725104. 725104. Or this one. 725108. We pop him. 7. Seven two five. Okay. So this is recommended and for us to so one more job I'm running because this one is a smaller one. Training 5 sample product. Okay, here this particular thing has some problem. So here we need a more, which is sample is very less. Data is very less. So it's not running. 725104 will try. And try this one, AD1879, because this is 380 and you have more than 5 actives and 5 inactives. I think this is the best one. The size also smaller, so you can try 1879. This library 1879. So I'm trying this one. This model. That's that one. Since it's 2,90,000, it will take more time to build a model. So this may actually work faster. Since we're doing a demo, this may work faster. Meanwhile, what you can do, you can go and learn here, like know more about how it works. So how to set up, you can go and learn here. Manual is there. So this is how the results you get. Yeah, finally, you will, after running virtual screening, you get this one. After model is built and then you do virtual screening, from that library, a few formats will be selected and which are more likely to have activity, they will be displayed. This is not working. Okay, so this is the correct one. Why this is not working? I don't know. The server will be busy. Finally it's running. Yeah, it's done. Can you see here? The data file, target table file, model file, testing results file, all are there. Okay, so model file you can download. So you can store this. 1879_496. This one is stored. Save it. Testing results file. These are all different outputs. Target labels files. The data file we gave. Okay, now what you do? This job is over. Now come back. Now start virtual screening. Model is built now. Now choose model type. Model file. Upload model file. The model file you got now. Which one you got? Remember the P file, model file. This is a model file. Just now you ran and got a model file. Okay. So the model file, we built a model and we were giving the model file and then upload PubChem CADs of chemicals to be screened. This is the library. Okay. So PubChem CADs means like the different so what you can do, you can try the different drugs. Okay, so you can take different drugs and you can give. So now this can be got from the study itself. If we go to the study now, the study, those active compound CADs will be given. Compounds active. The index. Can you see? This is the ID. So these are the active compounds. So their IDs you have to provide line by line. So you have to create a file and you have to do that one. So what we can do, we can make such a file. Okay, so what you can do, you can go and use this ID, PubChem ID or some ID. Okay, so it's there. So assay data is there. Okay, can you see here the data file, data table? So can you see CAD is there now? Okay, so the CAD is there. You can copy the CAD, all these numbers, line by line. So you can create one file. You're asking now. So VI CAD, like you can find the CAD list. So we can use this one. Okay, these are all actually already tested one, based on which we build a model. So what we can do, we can try some newer ones. So what I'm going to do, instead of using the already known ones, I'm going to use the some new ones. Okay, so I'm going to get CAD from CAD. Or what you can do, you can just select some few from this list, 3162 316283 316283 316 yeah. So like this, some few comments I'm going to give CAD randomly. So some are all active. So, 761840 761840. Okay, all actives. Now if we go actives. Yeah, so we can take some inactive 951 951 610 951 610. Okay, so I'm just trying to screen some molecules 1214 257. Okay, 4257. Then maybe I can take like this lopinavir like this. What is CAD number of this one? Yeah, it is. Any idea what is CAD of lopinavir? Lopinavir. Yeah. Okay, my CAD 927 92727 92727. 92727. Okay, then I can try nelfinavir. Just nelfinavir or any other compound also can try. Nelfinavir mesylate. Okay, 64143. 64143. 64143. Okay, so I just made a small file, CD list. Okay, so I'm going to use this one in my screening. Choose file. So what is that one which I made? CAD na CAD list. Okay, now build distribution graph. Yes, email optional, screen. See, I am using a very small number of commands just to demonstrate, but we have to use a large library. So the purpose of which screening is to use a large library for screening. Just for demo purpose, I'm using some small built library with some few commands. Any doubts you can ask? There are more. So when it's running now, we can just see some videos related to our. For example, the alpha fold, the initial one, that's a detailed video available. Alpha fold. So this is a very detailed 1 hour video from the Alpha Fold person itself, from the DeepMind company. This one.
Right, thank you very much. And thank you for the invitation to speak here. So this is work on protein structure prediction that I worked on with all these colleagues at DeepMind, and including David Jones from the CRIC and UCL, who sort of got us started in protein folding. And this is work that's described in two papers. One, we had a paper in Proteins last year, which describes a sort of more complete system, which describes a number of other machine learning techniques that I'm not going to go into details about here, including some generative models and some more reinforcement learning approaches, but this is more of a supervised approach. We combined several different systems to enter a protein structure prediction assessment over a year ago now, and basically here I'm going to focus on the work that's described in a paper that came out last week and is, I think, in print as of Friday this week. So I'm at DeepMind. It's known as an artificial intelligence company, and basically our mission is to solve artificial general intelligence. That's the more than specific focused AI, but having a more human-like intelligence that can be applied to many different problems and sort of reason about problems. But the second line of our mission statement is to use it to solve important problems. And in particular, we now have a science group where we're trying to apply the techniques of deep learning, machine learning, and AI to solve fundamental science problems. So we got into protein structure prediction partly because it's a fundamental problem in biology, but it has very clear goals and rich data. So as sort of people with computational backgrounds, then it was a very amenable science problem that we could work on essentially purely computationally. And if it's a very important problem that if we can advance the state of the art, then we can have a lot of downstream implications, applications to all kinds of areas of biology in understanding things like protein interactions, protein function, and understanding the processes of life. So a little bit of background. So proteins are the fundamental building blocks of life. They're involved in just about every process in living organisms, whether that's providing structure, catalyzing chemical reactions, transducing signals, transporting molecules around the cell, or of course in the immune system of antibodies are a kind of protein. So also for drug discovery, they're very important. They're the targets of many drugs that you're trying to, say, get small molecules to stick to proteins to adjust their function. And they're a class of drugs, and things like antibodies can actually be biological drugs. And one fundamental thing about proteins is, to a large extent, the shape of the protein tells us about the function. The way it folds up and the way the sort of reactive sites on the protein end up on the surface or in the core, that's going to determine the function. And just as an example of how the amazing things that proteins do, this is effectively a motor that can, I think, run in two directions. It can either synthesize ATP or it can use ATP and turn into a pump. But this is made up of proteins, multiple proteins.
He's telling about this F0, F1 ATP synthase, one of the molecular motors, very sophisticated protein assembly. The architecture of this protein resembles like a motor, where it, across the hydrogen proton gradient, it churns out ATP. So
proteins that combine together, but there are billions of these inside your body are active all the time. So the protein structure prediction, it can be simplified as this top image of, we go from a sequence of letters to a three-dimensional structure. So proteins are these chains of amino acids. Amino acids are sort of small fundamental molecules. We have a library of 20 of them, essentially. So we represent them by letters of the alphabet. And then they are polymerized into these long chains with different combinations of amino acids. And the identities of those amino acids determine the particular properties of this protein, and the way it folds up into its shape and displays these different amino acids with determines the function. So we can model a protein by the backbone, the way it's polymerized. It's basically each amino acid contributes a nitrogen and 2 carbons to the backbone. So you've got this regular repeating structure of nitrogen, carbon, carbon, nitrogen, carbon, carbon for each amino acid. So that's represented by a path through space, this chain, which is the red line in my three-dimensional structure there. And then the side chains are these functional groups that are different for each letter of the alphabet. And they're represented by the thin green lines coming off the red backbone. So those are the side chains. We would also like to know the exact geometry of those. So the problem that we're trying to tackle is going from a string to a set of three-dimensional coordinates, at least one per residue, per amino acid, but ultimately the coordinates of every single atom. And we want to do this partly to understand the function. And there are experimental techniques. For 70 years, people have been working on experimental techniques to solve protein structure, originally X-ray diffraction, but also NMR and cryo-EM is the most very popular these days, but they're still very difficult and expensive. You can spend many years and a lot of money with these pieces of expensive equipment trying to get your protein to crystallize and then actually get a successful image that you can turn into a three-dimensional structure. So people have been doing this for a number of years, but it's still very difficult. And if we have a new protein, then we would like to be able to just know the structure immediately, ideally computationally. So just to give a little bit more detail, we're trying to get the atoms of particularly the backbone atoms, the coordinates, and we can represent the geometry of the backbone with torsion angles. So in this image on the right, you've got these rotations with the phi and psi angles, and they completely determine the structure of the backbone. So we have basically, if we have n residues, amino acids, then we'll have 2n degrees of freedom, these psi and phi angles. That will capture the structure of the backbone. And one thing that we'll come to later is we built a differentiable model of the protein geometry that basically maps from those torsions, phi and psi, to atoms' positions of the backbone. And the differentiable nature of that becomes in handy use later. Another representation that we can use is the distances between those residues. And in particular, we pick one atom for each residue. We take the carbon beta, which is the first atom on the side chain. So in this rotating model here, those are represented by these short cylinders sticking off the main path that's traced out. And the structure of those atoms is completely represented by the matrix of distances between pairs of those atoms. So if I take any two residues labeled I and J, and I measure the distance between them in this 3D model, I get a matrix, the distance matrix. So it has n squared distances. That completely captures the structure of the backbone up to a symmetry, and it is a useful representation that we'll come back to later. And in particular, on the left, I've chosen one particular C beta atom, and then I've drawn lines to all the other C betas that are within 8 angstrom distance. And those correspond, that corresponds to one column of this distance matrix.
Yes,
and it would be
distance matrix, and why is using a 8 angstrom cutoff is because most of the non-covalent interactions, like electrostatic interactions, basically, they fall within that 8 angstroms. Okay, so when it's far away, more than 8 angstroms, it will become too feeble. So they give cutoff at 8 angstroms and then calculate all the atomic interactions. Okay, non-covalent interactions, electrostatic interactions, hydrogen bonding interactions, hydrophobic interactions, this van der Waals, all those things. Okay, so he's making a distance matrix within the residues, inter-residue distance matrix.
The bright ones are the ones that are closest to the particular atom. So as an aside, I'm going to talk a little bit about deep learning. So essentially deep learning is about neural networks, particularly neural networks with a lot of layers. But neural networks have only been known to be these universal function approximators, where you map from some inputs into some outputs, and you're training them to optimize some objective. And in particular, you're training it so that your outputs are the desirable outputs and match the outputs that you give it when you have a training set. So the objective is the closeness of match between the outputs that you get from your neural network and the true outputs that you know from labeled data. And you can optimize these functions by methods like gradient descent, which basically tweak the parameters of the neural network such that it computes a good value for the objective and predicts the outputs that you want. And of course, they've been hugely successful in recent years, applied to all different kinds of problems. Before working on proteins, I worked on speech recognition and speech synthesis in particular, but they're also the best class of models these days for things like machine translation, image recognition, and segmentation. And what DeepMind's applied them to in particular has been playing games. So having agents, these are systems that act in some kind of environment. And we've focused on these simple environments of games where there are very limited set of actions. And you've got very clear rewards telling you whether you're acting successfully. But then we've applied it to more and more complex kinds of games, originally starting with these Atari video games where you only have, say, left and right actions, maybe, up to StarCraft, where you have lots of actions and a very complex environment that is difficult to understand and limited information. But now, successively, we've applied these agents to get state-of-the-art in all these different kinds of games, including Go and chess as well. And the advantages of neural networks is that they're capable of modeling very complex data, in particular dealing with these long-range, subtle patterns where there's maybe a lot of redundancy in the data, and you need to generalize from examples that you know what the right answer should be to examples that you've never seen before, and you have to infer what the correct answer should be. And in particular, the structure of the network gives what we call an inductive bias to certain kinds of modeling, where the way you create your network makes it better able to give the right kind of answers to the problem that you're tackling. And if you use the wrong kind of network with the wrong kind of architecture, then it will be much harder to train it to solve the task that you want to do. So why is machine learning appropriate for protein structure modeling? So, well, it's a very complex problem. People have been trying to do it for very many years. And it has these very complex interactions that we can't fully characterize by physics in a very simple way. You can do molecular dynamics simulations, but they take a very long time, and even so are limited in the accuracy. And in particular, with
actually a previous approach called folding at home. Folding at home was actually from Stanford University. Vijay Pandey and his group, they came with the distributed computing framework for running molecular dynamic simulations on carrier protein folding. But actually, that is limited to first very small proteins, and then it takes a lot of time also. But still, it's there. This distributed computing based on molecular dynamic simulations to arrive at the protein fold. Okay. But the thing is, it's limited to it's very time consuming, and then we need a lot of distributed computers. Okay. So in fact they use thousands and thousands of computers across the North American grid. So North American, Canada, US universities, they utilize those idle computers, and then this distributed computing called folding at home. We can go and type folding at home, and you can see this. So, but this AlphaFold is superior to that because you don't need a distributed computing framework here.
Proteins, we also have both local and long-range dependencies, that the local residues interact with each other, but the protein can loop back on itself, and things that are a long way apart in the sequence, in the alphabetic string that we had, can actually end up being physically very close. So that's a long-range dependency. One other major advantage is there's a lot of data. Because of those 70 years of people solving structures with X-rays and cryo-EM, there are now 150,000 entries stored in the central database, PDB. And basically, it's a condition of publishing a paper about when you find a structure that you deposit it in this database. So we've got lots of training data, although it's not of the scale that we're used to for things like speech recognition and image recognition, because it's very redundant. There are many repeats of very similar structures. So we end up reducing this 150,000 to about 30,000 different examples that we can use for training. And the final advantage for solving protein structure modeling with machine learning is that there's this CASP assessment, the critical assessment of protein structure prediction, that every 2 years does a blind assessment of the state-of-the-art performance of algorithms. It's been going, there have been 13 of these over 26 years, and basically they hold back structures that are newly being solved by experimental methods and apply the latest structure prediction algorithms to those proteins, and then assess the performance on those proteins where nobody who's entering the competition has seen the structure.
So you can, yeah, you can actually watch this.
So I'll take a step back and talk now about one of the sort of fundamental principles behind protein structure prediction, which is to use protein co-evolution. So this is something that has been known about, certainly since the 80s, as a possible clue for solving structure prediction, and has been quite influential in the last, say, 8 years in terms of actually having an impact in improving algorithms. So the argument for protein co-evolution goes like this. So DNA sequences encode the proteins, but they're constantly mutating over time. And if we think of the tree of life as this diverging structure of different organisms, as organisms diverge, then they will inherit the proteins from their ancestor organism, but those proteins will diverge over time. So also, protein space is so large, as Jennifer mentioned, it's a size 20 to the n for a length n protein. So the chance of getting two similar sequences just by chance is very, very small. So if you find two similar sequences, then the chances are they are related, they came from a common ancestor, and that they will have a similar structure, in that structure determines function, and function is likely to be preserved over evolution because it's required for survival in protein folding.
Abraham, sir, can you enable chat for me so that I can paste this URL to the students? Can you enable the chat for me? The chat is locked actually. It's disabled for me. Hello? Somebody there? So what I say is, since they want to wind up by 5 o'clock, and you can watch this video. This is a highly technical video about AlphaFold from the DeepMind person called Andrew Senior. So what you can do is you can go to this URL. You can go to this URL. I just wanted to paste this URL here so that the students can, like go there, but you can write it down. So this is the URL. So YouTube, yeah. So you can go, otherwise you can type AlphaFold improved protein structure prediction. It's a very recent YouTube. So you can go and watch the full YouTube video and get insight. You can also mail to us. Okay. Sir, Abraham, sir, why can't you enable chat for me, sir? Hello, please. You're there, sir? Hello? Yeah. So this is the URL. Now it's come. Okay. So YouTube watch, you can go watch this URL. And any queries related to this workshop, now you can mail me here, wisecornerlabs@gmail.com. Okay, so you can mail me any queries related to this AI tools or any kind of future you want to work with us related to this machine learning, all those things. Similarly, you can visit our website, wisecornerlabs.com. Okay, so this is the one. Because of time is not there and they want to close the college now. So the thing is now it's already 5. So what you can do, no problem. You can mail to me, or you can even call me and talk with me. Okay. So I already gave you my email ID, wisecornerlabs.com. wisecornerlabs@gmail.com. Okay. So any queries now you can post it here. So the thing is, like the output of this result now will take some time. So finally you will get the results, but it may take some time. Still the job is running, okay? Because already the model has been built, but now it's trying to predict. Okay, so since we are used to slightly stringent conditions, it takes a little time for the prediction. Okay, anyway, like if you use the other servers now, it may take 2 weeks, 3 weeks to give the results. Okay, but this one will take matter of hours, or maybe like 1 or 2 hours maximum. Okay, so what you can do, you can use this deep pubchem, which is really a very good tool, and also you can use this other tools like deep screening and AlphaFold, and for AlphaFold you use for what? So let us summarize now. AlphaFold you use for target structure prediction, because when you are limited by time and you want to really get the structure of the target protein in quick time, so you can use a predicted model. Okay. Second thing, once you have the structure in hand, you can do virtual screening using these tools that I mentioned: deep screening, deep pubchem. This kind of virtual screening service can be used. Third thing is you can also predict the molecular properties of the drugs using the chemprop or the thing. Then you can even synthesize that molecule. Once you have a molecule in hand, which can be promising, you can synthesize the molecule. For the synthesis, we can use this ASCOS, MIT-based ASCOS tool for having a strategy, retrosynthetic strategy that we discussed yesterday. Okay, so with all these things, really you can accelerate the drug discovery for COVID-19. Okay, so again, only thing is we have to explore these ones. Okay, so thanks a lot for the patient hearing. Any doubts you can always you can mail to me. Okay, yes, thanks a lot. Yeah, sir. Sir, we can wind, sir.
Thank you, Sahul sir.
Thank you, sir. Sir, I have mailed you that thing, sir, that you can hand out. You can give to the participants, sir.
Yeah, done, sir. We'll send you, sir. Thank you, sir. Hello, participants. So here is a small video. So there is concluding remarks. So given by our honorable chairman. Sound sir ఇందాక మాట్లాడినది ఇప్పుడు వస్తుంది. ఓ నా వాయిస్ ఇప్పుడు నేను మాట్లాడింది ఇప్పుడు వస్తుంది. షేర్ సౌండ్ ఆన్. పెట్టు
I am happy to learn that our biotechnology department, headed by Professor Krupanidhi, Professor Venkatesarlu, and Professor Abraham, conducted a conference on contemporary issue, that is artificial intelligence tool for accelerated drug discovery recently, and today is the conclusion part of the conference. At the outset, I thank the guest lecturers, Hulen, University of Kansas from America, and other guests, Shahul Hamid, for their valuable speeches and for their valuable deliberations. This is a very interesting topic in the recent times, and it is a very contemporary topic. So AI, artificial intelligence interfering in the drug discovery. And this is the future actually. There is a lot of interference of artificial intelligence, machine learning and in the health. So in the future, so the health would be totally personalized. Every individual genome or DNA is mapped, and the drugs are defined, and drugs are given as per their DNAs. So in that situation, conducting a conference on this topic is very interesting, and I thank all the participants. I learned that the participants are from many countries, from Malaysia, Singapore, and other Dubai and other neighboring countries, and there are more than 100 participants from different universities, from different countries. So yes, they must have got extra information of interference of artificial intelligence into the biotechnology. So they must have got lot of benefit out of this conference. Yes, in future also I request the professors to work more in this direction. This is the, as I told you, this is the future in the health area. And now the same drug is applied for different people of the same disease, but hereafter the drugs would be different for different people based on that, their DNA. I think this will be done in the next 4 or 5 years, and an initial drive. And holding this kind of conference is a very happy part. I wish that the guest people should conduct some research on this, and also I will be more happy if our department would be participated in that kind of future research. I thank one and all the participants, guests. Many companies world over are trying to discover the drugs for COVID. I wish the drug will come out very early. But the whole problem is this drug should undergo lots of trials. So anyway, any drug gives the confidence among the common people, because most of the people are suffering more than the corona, suffering from the fear. So to remove this fear, even the normal drugs also may be sometimes helpful, but very specific drugs also, they are in the pipeline. And in India also, the Bharat Biotech and other people are doing it in a very accelerated way. I hope and I wish that drug should come out as early as possible, so that the whole humanity will be happy, and also come out of this pandemic. Recently, Russia has given one drug and it is applied to the daughter of the Russian president also. Similar drugs should come out from India also for in a cost-effective way. Some company, Bharat Biotech, has announced we are going to prepare a very cost-effective drug which is almost equal to the cost of water. So this is a very welcoming step. I hope and I wish these drug companies will take care of the cost effectiveness, especially in India, and come out very early, and trials should be in a large way so that there won't be any side effects on this. So this they can take the help of artificial intelligence in the trials also, in the testing pattern also. I wish all these companies should come out very early to save the humankind from this pandemic. And really congratulate the biotechnology department headed by Venkateswarlu and Krupanidhi. Thank you very much and wish you all the best.
Hello, Sahul. Hello, Sahul sir.
Okay, sir. Hello, sir. Yes, sir. Please.
Yeah, Sahul sir. Thank you, sir, for your
Thanks, sir. Thanks, sir.
cooperation.
Thanks for giving this opportunity for conducting this webinar
Sir.
series. Maybe in future we can conduct more, better workshops.
Sure. Thank you, Sahul sir. Your support is very much required, sir.
Yes, sir.
Yeah, dear participants, thank you all for sparing your time. So now we are closing this 5-day international online workshop. So we have successfully conducted by the cooperation of our management, VIGNAN'S Foundation for Science, Technology and Research. And we also express my deep thanks to the Professor S. Krupanidhi Garu, who is head Department of Biotechnology. So he is all over with us. So his support, without his support, we may not execute this program. We thank you, sir. So the 5-day schedule, it went on well. So the program, it can be begun by a keynote talk by Dr. Ho Liang, Associate Professor from Kansas State University. So he has given a talk on AI-driven drug discovery for COVID-19. So I think all faculty participants and research scholars, so they must benefited the knowledge shared by our keynote speaker by name Professor Ho Liang sir. So the sessions followed by our resource person, Dr. Shahul Ahmed sir. So he is the director of Vice Corner Laboratories, Chennai. So sir has given an elaborated talk and he has emphasized on different AI-based tools in 5-day program. So the day 1, so Sahul Hamid sir, so he spoke about the deep screen tools. So he also given some basics about the Autodoc. He gave demo. And the day 2, he mentioned about the ChemProp, a machine learning based tool. And day 3 followed by the theory and basic concepts on neural networks. Again, day 4 by Sahul Hamid sir. So he has given a talk on ASCA's databases, so which contain the different modules. And day 5, again the talk and today's talk by Shahul Hamid sir. So he has given a talk on linear regression models, and he also given some insights about the Jupyter notebook and also a deep PubChem. So the deep PubChem, it is very much essential for QSAR prediction. So we thank Sir Shahul Hamid sir and Ho Liang sir. So we have allowed the 100 participants. So the participants are from so other than India, we have participants from other countries like we have participants from Egypt, Malaysia, America, Nigeria, Palestine, and also many university faculty and scholars from India. Even we have participants from CSIR Lucknow. We have participants from IIT Jodhpur. We have similarly participants from Hyderabad Central University and also WIT Vellore and many institutes in India. I think all participants must have benefited. I once again thank you all for sparing your time. So if you have any queries, you please send an SMS to our organizing secretary, Dr. Abraham Pillay, and also directly to the Shahul Hamid sir. So they will clarify your doubts. So Dr. Abraham Pillay is the organizing secretary of this workshop. So he is the man behind this workshop. He only created all the links and he managed, he hosted all 5-day sessions. So we thank Abraham Pillay sir, organizing secretary of this workshop. So with this, we are closing the 5-day online workshop. Thank you. Thank you all. Thank you, Shahul sir.
Thank you, sir. I use this opportunity to thank the management of Vignan University, which has been doing a wonderful job of conducting several workshops related to COVID-19. And I also appreciate the efforts taken by Venkateshwarlu sir, the deputy head, and the dynamic person, Abraham Pillay, assistant professor of Vignan University, and also Professor Kripanadi, HOD of the department. So also thank the chairman and other management staff for providing this opportunity. So I think like in the future we can see more sessions. Yes.
Thank you. Thank you, sir. Thank you, sir. All of participants. So now the participants will share the feedback link. All participants will get the e-certificate. So this feedback link is active up to 6:30 today. So the feedback link, again, I'm repeating, it is active up to 6:30 p.m. today. So please, all of you submit your feedback for getting e-certificates. Thank you all. Participants may leave the meeting now.